So let's recall that for option pricing in Chapter 10 and 11, we had different drift assumptions. The one that the author most often uses is the one that was originally given in Formula 1010. And that's the formula where the drift in the price, the return, is R, the risk-free rate, minus the dividend rate delta. So this was related to the forward price of the stock, and this was the most commonly used. But it was also noted in Chapter 11 there are other models for the binomial which are equally useful in pricing options. And one was in a Formula 1118, which was referred to as the Cox-Ross-Rubinstein model for the binomial. And there, the alpha binomial was 0. There was no h term. There was only the square root term. And then finally, there was what was called the Lognormal model, the Lognormal binomial model, which seemed to be an unusual term at the time. But in fact, we can see that the functional form of the drift term, the coefficient of h in that so-called Lognormal binomial model, has exactly the same functional form we're assuming in our current Lognormal model. Again, notice that we're using R instead of alpha because we're building binomial models to price options. We're not building binomial models to price or to develop real-world stock prices. But I note at the bottom here that if we do want to develop real-world modeling, we just convert the R in the binomial model to alpha, and we can create a binomial model in the real world of stock prices, where we use the alpha instead of the R. So in option pricing, the Z gets, when we go from the continuous log-normal distribution of prices to the binomial model, we go from a Z to a plus or minus 1. But there's a probability distribution that's important. What is that binomial probability distribution? And what we saw is that in option pricing, the Z of the log-normal distribution becomes a plus or minus 1, and the probability depends on P star. In other words, you could think about that Z becomes 1 if we drew R as uniform 0, 1. So you could imagine that if we were building a binomial model and we wanted to know, gee, at this node, do I go up or do I go down? A simple way to do it is to draw a uniformly distributed random variable between 0 and 1. And if that uniform variable is smaller than P star, the risk neutral probability, we go up. We use a plus 1. If it's bigger than P star, we go down. We use a minus 1. So and we'll see this in Chapter 19 in more detail. But this is how we would simulate a path of prices through a log-normal lattice, a binomial lattice. This is how we would, let me correct that. This is how we would simulate a sequence of prices in a binomial lattice. At each node, we have to make a decision, do we go up or down? And we can simply draw a uniformly distributed random variable, and depending on how big it is, it tells us whether we go up at that node or down at that node. If we're, and P star is the familiar formula originally given in 10.5, which is the risk-free return adjusted for dividends minus D divided by U minus D. So in the various models where the U and the D differ, P star also differs. And so as we build binomial models, we will make our decision to go up or down differently depending on what we assume about U and D. In the real world, it's typical that, that Z will be plus 1 or minus 1 with equal probability. So as I said earlier, we have an expression for U is e to the alpha, I'll just call it b instead of bin for binomial h, plus sigma square root of h And our typical model for the down return in the binomial is e to some alpha b h minus sigma square root of h. And the alpha b's will depend on which of the various chapter 11 or 10 models we use. Notice that no matter which of the models we use, that if you look at the ratio of u divided by d, that ratio is always e to the 2 sigma h. So while the definition of b varies in those earlier chapter models, notice that the ratio of the up return to the down return is always the same. It's 2 sigma, sorry, there's a square root here. It's 2 sigma square root of h. The point I just made a moment ago then was that because p star is defined as e to the r minus delta h minus d over u minus d, that as I use different alpha binomials, the u and the d change, and so does the p star. And it's because of that connection between the u, the d, and the p star in these various models that it may or may not surprise you that all of those earlier binomials, when the time interval gets small, they all converge to the same binomial model, namely the binomial model we now study. What we have is that all the binomial models all converge to the same log-normal model. And it's the log-normal model with the parameters r minus delta minus a half sigma squared t and variance sigma squared t. Even though we start with different u's and d's, because the p star also varies in those earlier models, that as the time interval in the lattice gets smaller, all of these binomial models converge to the same distribution of stock prices, namely the distribution which is log normal. And now notice that I have an r here. As I mentioned earlier, in all of our log normal modeling, we expect to see an r, not an alpha. And all of the alpha bins reflected r, not alpha, and they converge to a log normal that reflects r, not alpha.